sure that this briefing is available for everybody. So we're going to record it and put it on the FDL website. But just please be aware of that. And then similarly, hoping that you, once you've seen the work that we're looking to tackle this year, that you forward this to researchers or individuals that you think might be interested in supporting us. We still have 1 week before applications close, and we still are looking for specialists to help us tackle some of these problems. So a little bit of an overview about today. A quick introduction from me. My name is James Parr. I run Trillium, which co-hosts and co-runs FDL with the SETI Institute in Mountain View. And then we're going to change gears pretty quickly and start talking about the science, which is sort of why we're here today. Heliophysics first, 2 challenges planned for heliophysics, then planetary science, the moon, earth science. We have 4 earth science projects this year: lightning extreme weather, a knowledge discovery framework, Earth Intelligence Engine, and Where Droughts Are Born. And then 2 astrophysics challenges, Star Check and Star Spots, and then 1 Space Medicine Astronaut Health challenge, which we'll do to wrap up. Then we're going to try and make sure we have time for a general Q&A. We want to talk about how we're going to tackle FDL this year in the likely event that we are running FDL virtually. Although I did hear on the news this morning that there's a new vaccine potentially out, so you never know. Or we might find that coronavirus is destroyed by UV and that we're all back to normal life by the summer. But certainly we're on the glide path to FDL being virtual, and we're making preparations as if it will be. So that's the overview of the agenda. I don't know if anyone's got any things they want to add at this point. And happy to hear any thoughts or builds.
Well, James, no questions at the moment, but I just wanted to say kudos to you and your team for moving forward through the COVID to a positive place and moving this forward. It's as seamless as I've seen. Now, I'm certain the devil's in the details and the tough times are ahead, but for my vote, this is the right step forward. Looking forward to what everybody has to say. Thanks
so much, Lynn. And we put a lot of thought into how to run this virtually, and fortunately we have a great faculty who's also been thinking about this, and we actually just did a faculty call, and there are a few innovations that we think are going to make a big difference in terms of how we get to the sort of veracity of scientific output, and we can talk about that later in the call. So sort of without further ado, just to, again, for folks that are joining us, and I know there are a lot of you who are joining who aren't aware of FDL or haven't been involved, a little bit of background. You may have seen the movie Interstellar, which drew upon this inspiration, but this is from the summer studies in the late 70s, which were held at NASA Ames. And this was really the starting point of FDL, was the idea that actually meaningful work for NASA could be done by creating focus and creating smart people and bringing them together over the summer. And the idea of a summer study was something which NASA had done to great success before, and this study on Island 1 by Gerard and Neil was the output. And really we thought, well, listen, let's revisit that. Let's do it again, but let's add in the added ingredient of machine learning, and that's really where FDL started. And over the years, we've migrated and started to figure out exactly, why FDL should exist and why it should integrate within NASA's innovation portfolio. And really, the first thing is to bring the right people to the problem, and we sort of believe that machine learning is a bit like the way that Hollywood makes a movie, is that Hollywood has a script, if you like, the challenge, and then the right people are brought together to bring their talents to bear on this problem. And this is we believe is a really successful model for doing this sort of accelerated research. We're also looking to push best practice in machine learning. And if you are a machine learning person, you know, a lot of the methodologies are becoming democratized, and we're very interested in pushing state of the art. We want you to do published research, work that you can integrate to your own studies. And so we're sort of interested in migrating away from, if you like, classical supervised machine learning and into unsupervised problems that have sparse or unlabeled data, problems that require a lot of investment and explainability. And then the other thing which we're wanting to build expertise in, and really leadership, is reproducibility. So this idea that if you're interested in ethical AI, or even if you're interested in AI that's going to be trusted in a deployed scenario, like, you know, landing in the lunar poles, you really want to have 100% understanding of the math and the processes that have gone into making that machine learning work. And so we really want to lead the charge in terms of making reproducible workflows. And this is a theme which you'll hear a lot over the next, you know, as you join the FDL family. The other thing which is sort of worthwhile thinking about is that FDL is a year-long program. It starts in January with the development phase, where we work together to get to the challenges, which we'll share in a moment. We are, as you can see here, the little red dot, this is where we are at the moment. We're at the process of team alignment, which is why we're briefing everybody on the challenges at the moment, and we'll and hopefully this will be inspiration for you to sign up and apply, or forward this to somebody you think would be particularly suited to these problems. And then we go into setup, definition of the problem, data ingestion, identification, alignment, really getting everything sorted out. So when the teams are aggregated over the summer, everything is set up, and we can press go on algorithm development and getting those machine learning pipelines worked out. And then, of course, we ask the teams to produce papers and outputs, and take that work to AI conferences such as NeurIPS and AAAI. The other thing which we're learning about is how to do enhanced data products. It's not just about algorithms. We want to have enhanced outputs. Like last year, we produced, one of the teams produced a lunar resource map of the moon. This is a very useful output of a machine learning project. We're looking for those sorts of outcomes, and then ultimately also APIs, so AI as a service, which may inform missions in the future. So again, a little bit of difference about FDL this year is we're going to have the sprint, which is going to follow the normal 8-week summer timeline from the Monday 22nd of June to Friday 14th of August. But we're also going to have a 4-week lead-in and the boot camp over between 25th of May and 19th of June. And so this is a new innovation, which is part of FDL becoming virtual. And the idea is that in this lead-in, we'll do a lot of the work in data prep and a lot of the work in sort of building those interpersonal connections that we believe are required to do exemplary outcomes.
James?
Yeah.
Yeah, it's probably worth mentioning here as well that not only is there this upfront phase, if you can stay with that schedule for a moment. Yeah. Not only is there that upfront 4-week period that James has described, but what we've done is also move the boot camp, which usually happens in the first week of the program, into that lead-in phase, which it has the effect of adding a week to the sprint phase itself. So instead of the sprint phase being a boot camp followed by 7 weeks, it's a full 8 weeks where we bring the boot camp into that front end period, which is all about, you know, data preparation, challenge refinement, team integration, et cetera. So this is an important part of what will constitute, we think, an effective virtual program.
Thanks, Bill. So again, I don't want to spend too much time on the preamble, but perhaps it's nice sometimes to celebrate where we've been. This is a diagram that shows our machine learning or AI portfolio. over the last 5 years. And you'll see here we've been focusing on heliophysics, living with the star, the moon for good. We have a number of projects to do with the moon. We've done 4 or so projects in planetary defense. We've done 3 or so in astrobiology, Are We Alone? And numerous ones in earth science and the mission control for the earth theme, and astronaut health. And so we're starting to build capabilities and faculty around all of these domains. And FDL's, you'll see there's a sort of, if you like, there's a sort of, the concept is that we sort of create a cone of expertise around these domains. And we like it when the project is sort of building off of where we've been, and we can talk about more of that another occasion. But I just wanted to give you a sense that that there's a sort of gestalt which is all working in this sort of joined up way. We're really interested in outcomes, scientific outcomes that are useful for your careers. We encourage teams to publish their results in scientific journals, peer-reviewed scientific journals, but also take them to conferences such as AGU. We had 6 papers presented at AGU last year, and there's Bill at the FDL stand. And then also at NeurIPS. If you aren't a machine learning person, you might not know, but NeurIPS is essentially considered one of the top, if not the the premier academic machine learning conference. And it's very well timed that it's in December. So that means that our teams have time to produce papers and get them submitted into NeurIPS. And last year we had 12 teams present at NeurIPS. And the Clouds team actually won Best Paper at the Climate Change Workshop, which we're obviously very proud about. FDL is a public-private partnership, and it works because it's this sort of synthesis between academia, the needs of space agencies, but also the capacities and capabilities of our partners. So Google Cloud, Intel, AI, IBM, NVIDIA, all providing machine learning capacity. And then we have partners such as MIT, Lockheed Martin, Mayo Clinic, USGS, and the Luxembourg Space Agency. And then specialist AI companies like Augustus and Element AI. So I wanted to sort of do a shout out to our partners. They're very much an important ingredient in making this work. And in fact, we couldn't do it without them and the expertise that they bring. And you'll be working shoulder to shoulder with experts from these organizations if you join us this year. So perhaps worthwhile changing gears, just in the interest of time, to talk about the science. And this is a reminder of the dates for you if you need to make a note. The on-ramp time will be between the 25th of May and then the Friday, the 19th of June. And that last week is when we'll have the boot camp, as Bill mentioned. And then the actual sprint itself will be the 8 weeks from Monday, 22nd of June to Friday, 14th of August. And of course, we compensate you for that period. So I wonder if we change gears and start talking about the work. And we've invited our faculty to just give a sort of taster of each challenge, just sort of a few minutes, just so you can get a sense of what the opportunity is. And I'd like to give the microphone to Asti.
Hi, good morning, everybody. I'm happy to kickstart this briefing. The challenge that we are proposing this year is tracking the geoeffectiveness of solar storms. Now, the core of this challenge is that interaction between solar storms and the terrestrial space environment produces a variety of impacts, which are not all equal. So some of them produce noticeable effects only at high latitudes, like amazingly beautiful northern lights, while others create a global effect, which can create effects like knocking out power grids and affecting communication systems. The key here is that there is a huge variety in properties of the solar storm, including solar wind, density, geomagnetic conditions. All of these enable the coupling of solar energy to the Earth's magnetosphere-ionosphere system. So for example, sometimes a really slow but really dense solar wind can produce a much bigger impact from really fast and less dense solar wind. The challenge is that we don't really know what combination of things actually result into what combination of effects. And that's what we are trying to address here. We want to investigate how well can we categorize the combination of solar wind and geomagnetic parameters that produce this impact on terrestrial systems. So for that, we will need data both from the sun, the space environment, and the ground to tackle this challenge. We will use NASA's Heliophysics system observatory data to characterize the solar wind and geomagnetic conditions. And we will also need information from ground-based observatories from multiple latitude regions on the Earth to characterize terrestrial impact. We know that there are several tracers of global scale geomagnetic activity, and there are several global instrument networks that observe the impact of a geomagnetic storm. They measure electron density or total electron content. They measure magnetic perturbations. They measure expansion of how big the auroral oval gets, etc. The idea, or the big idea here, is to figure out a superparameter that may be a combination of some of these tracers that tells us about the geoeffectiveness. And that is where the machine learning comes into picture. Most of the heliophysics system observatory and the ground-based observatories, they are taking continuous data. And we have data from now multiple solar cycles in this spectrum. So the challenge is, how do we effectively use this data to characterize this spectrum of conditions and figure out the superparameter of the tracers that tells us which storm or which conditions, combination of conditions will produce which combination of effects. It could be, we can start that as a simple classification problem for a single ground-based tracer, but the main phase would involve a deep learning solution to find this combination of superparameters. So I hope that makes sense, and I'm excited to be part of this challenge once again. And maybe we'll see many of you participate in the challenge going forward.
Awesome. Thanks, Asti. I don't know if anyone's wants to quickly ask a question now. We'd like to try and keep the cadence pretty high on these challenges as we go through them, but we have got time if anyone's got a pressing question.
James, I'm going to answer some of these questions that I see coming up in chat, just so we can keep the momentum going on the talk. Perfect. So the ones that I can get to, I'll try to, and awesome. We can get to others offline, and Zoe and others can help with that.
Thanks, Bill.
Sure.
Anyone have any questions for Asti?
James, not necessarily for Asti, but maybe if you could guide us on what kind of feedback would be most useful to you, or are you asking about technical questions related to the science topic at hand?
Yeah, I think as we go through the challenges, if you are somebody who's interested in this problem or wanted a little bit of sort of calibration, this would be the moment. As I say, we're going to have a Q&A at the end where we can go through, if you like, how FDL works and process stuff. And similarly, Bill will be on the chat. If you have FDL process questions, feel free to ask them. But I think at the end of each challenge, if there's a question about the science that you want to delve into, or how the data works, or this is the moment to ask the faculty member while they're here.
You can also use the chat to speak to a specific person, so you can direct a question to an individual by selecting that individual in the chat platform.
Thank you.
If there isn't any more, why don't we jump on? Thank you so much, Asti, and Miho. Let me give you the microphone for this one.
Hello everyone, so I'm Miho Janvier, and I'm a space physicist. I'm based in Paris. So the challenge, the earlier detection of solar wind characteristics, is basically kind of complementary to what Asti has just presented. And as Asti said, geomagnetic storms or magnetospheric substorms, so what happens on Earth, can lead to a variety of socioeconomic losses, such as, for example, communication systems being down or electric power distribution grids being down as well. So some of the causes of the geomagnetic storms or what we call the long duration of southward, so north to south, interplanetary magnetic field. So basically the magnetic field that is in interplanetary space, which is the space between the sun and the planets of the solar system. So we really want to determine this magnetic field and also the composition as well as the properties of the solar wind between the sun and the planets of the solar system. So we're interested in the intensity, the orientation of the magnetic field in the heliosphere, but also, as Asti said, we also want to know whether the solar wind becomes faster, because when the solar wind becomes faster, it can create a variety of processes that can lead to geomagnetic storms. And we're also interested in solar storms, which are kind of, if you will, giant magnetic clouds that are spurted out from the sun and they can travel in the solar system. So the challenge really here is about taking data from solar telescopes, and we actually already do have machine learning ready data sets, and we worked on that in previous FDL challenges as well. And we want to look at features that appear on the surface of the sun and the atmosphere of the sun, such as, for example, active regions, or common known to spread out solar flares or solar storm regions, or the regions of origin, coronal host, etc. So a variety of different regions of the sun that can lead to different solar winds that we can then measure in situ. And so I'm even thinking about bringing some magnetic fields modeling of the sun and link this with in-situ data missions at different heliospheric distances. And by using this combination of different data sets, we want to know whether we can predict from what we see at the sun, the conditions of the solar wind at different heliospheric distances. So different distances from the sun all the way to the Earth. And as I said, I think it's quite complementary to what Asti has presented, because, well, ultimately what we would like to know is, if we can see the sun, can we then predict the space environment of Earth or the other planets of the solar system, and therefore better predict geomagnetic storms or magnetospheric substorms? And if you have any questions, let me know.
Wonderful, thanks, Miho. Just while people are thinking, and I read somewhere it takes between 10 and 17 seconds to carve a real good question. We had in the chat, you may have seen, we had a question about what sort of data is heliophysics data. And you'll see this is from Ranak, is the data in heliophysics time series. And Asti, I don't know if you want to respond to that one.
Hi, James. I actually also responded on the chat that most of the heliophysics system observatory data that we are planning to use would be time series, but that cannot be said about the ground-based data. We will likely have a variety of different data that we have been using in the past challenges as well, that combines time series and geospatially resolved data into one model.
All right, well, we might jump on. Thanks to Miho and Asti. We're going to change gears now and start talking about the moon. This problem is supported by our friends at the Luxembourg Space Agency. And I'd like to invite Alison Zuniga from NASA to take us through it.
Hi, everyone. This is Alison Zuniga from NASA Ames, and I was one of the mentors on last year's Moon for Good challenge. And I'm working together with Dennis Wingo now in developing Moon for Good Phase 2. So we want to expand and build upon the challenge that was done last year, which was a really good challenge. We were able to do lunar resource mapping and develop a global lunar data stack to do this challenge. So we want to build on that, and then this year focus our work and attention at the lunar poles, where there is a lot of focused interest right now, because the lunar poles is believed to have a lot of large concentrations of water ice deposits at the poles. So what we want to do this year is look at the images from the poles. Last year, there was a lot of work that was done on thermal anomaly maps at the equatorial sites and locations. And the goal there last year was to identify potential areas of metallic deposits. So that's why we focused our attention on some of the craters in the equatorial locations where we thought there might be metallic deposits. So now we are extending that particular work and now gathering data and focusing at the poles. So what we would like to do is at the end of this, our goal would be to develop accurate 3D high resolution topographic maps. And we would like to center those maps at potential landing sites for water ice exploration. Like I said, there are a lot of missions, or a few missions that are planning to go to the poles. And one of those missions is the Viper mission that's pictured here. That's being developed by NASA Ames and Johnson Space Center, developing a rover to land at the South Pole and to look close to the craters, looking for hydrogen signatures, which would be an indication of water ice deposits. So we've been in communication with the team and asking them what would be very helpful for the Viper mission. And they said that, of course, producing higher resolution topographic maps at the poles would definitely be very much welcomed. The challenge of having these maps at the poles is that the images that we have now vary in lighting conditions. At the poles, the sun angle is very low. So a lot of the images are either in deep shadow, permanently dark, or a variety of shadows. So what we'd like to do are stitch the images with constant lighting, under constant lighting conditions as best that we can do, and that would help the Viper mission help in their traverse planning work. So there's a number of techniques that we could use for stitching and alignment of these images. And then once we do that, we also would like to produce thermal anomaly maps at the poles, and that would also help and identify potential areas where there may be large concentrations of water ice deposits. And then finally, we're envisioning to do a moon engine, which would be developing a platform where we can hold multiple layers of the lunar data and then have the algorithms built in so that you can pull up different maps and then be able to look at either topographic maps, thermal anomaly data, or other type of data. And it would all be a very friendly user environment and would be open to the public. So that is our vision for the Moon for Good Phase 2 for next year. I mean, for this upcoming summer. And with that, there's a question or two.
Yeah, thanks so much, Alison. Any questions about this one? I do realize that it's hard to ask questions when there's another 125 people you don't know online. And yeah, please go ahead.
Yeah, just quick comment. I just learned a few days ago the planet has a very large amount of moon imagery, but due to some restrictions about capturing things above the horizon line, haven't necessarily been able to be released. I've been trying to inquire if that can help somehow for the Moon for Good. It's probably mostly visual imagery, but I'm not sure if that can help with fusing data or anything.
That's a good comment. We can reach out to Planet. We were, of course, focused on the images that we have from LRO and looking at maybe Chandrayaan and other orbiters, but I haven't heard of Planet, so I'll follow up on that. Thank you.
Yeah, and I'm at Planet now, so I was just inquiring. I just learned this a few days ago, so I can. I was wondering whether more data will help somehow. Maybe not for this phase.
I think it's fair to say we know a guy.
Let's talk offline, but let's talk offline.
He's not trying to sell us data.
Sure, and I think you have my contact info, Brad, so we can follow up on that.
I have a question. So I use the Ames stereo pipeline to make elevation models of Mars, but it's also it's commonly used by the LRO community. So Ross Beyer at SETI and NASA Ames is involved with that project. And I was like, just looking, like there are some, I mean, they're incomplete, but there are some polar DEMs available from the USGS Astrogeology Center. So it might be good to interface with someone there because they're really involved with this high precision mosaicing of DEMs to make sure you get a lot of good alignment of the data. But then your second concern is, okay, how to scale out producing all the data that's already captured by LRO. So AIM stereo pipeline makes that tractable, combined with the cloud resources we have for FDL. Will be a good marriage, shall we say. So I would just encourage talking to some folks at the USGS to Astrogeology Center to interface with them to figure out what is sort of there already and what sort of things FDL time or the processing power to focus on.
Great. Yes, yes. Last year we did have a mentor from a guest mentor from USGS, so I'll definitely follow up on that to talk with them and see if they can contribute, hopefully with a guest mentor this year as well. That would be great. Thank you.
Thanks, Alison. We might jump ahead. There actually was a question on thermal anomalies from Ariel. I don't know if anybody could help answer that one, which is in the chat. But I think let's change gears now and talk Earth science. And this first one is lightning and extreme weather. This is supported by our friends at Lockheed Martin. And Clem, are you able to take the mic?
Might be muted. Clem?
Well, perhaps whilst we're waiting for Clem, why don't we jump to Rahul?
Oh, there he is.
Oh, there he is. Yeah, sorry.
Clem
Thanks.
here.
Yeah, let's get you back here. Oops.
I apologize. I was dialed in separately through my cell phone.
No problem.
So lightning is a very interesting data set. It tells us a lot about the inner workings of storm cells, and so it's a direct measure of the convective strength of a storm cell. And you can tell a lot of things from analyzing patterns in the lightning. It's sort of an X-ray into what's going on inside. So in comes my involvement. I'm with Lockheed Martin, and I've been working on weather satellites for quite a long time. And one of the newest and fanciest weather satellites that we have is the GOES-R series. It's a satellite in geostationary orbit, and it carries on it the geostationary lightning mapper. This is a high-speed video camera that detects lightning emissions coming from an oxygen emission line at 777 nanometers. So this light comes out of the top of the cloud and is perceived by the satellite. We see a tremendous amount of lightning, about 1 million lightning flashes every day. And traditionally, forecasters have used this data to help them predict what a storm will do next. So patterns in the lightning have been associated to severe weather outcomes, like in the most extreme case, tornadoes, but also large hail, high winds, flash flooding. So when they do their forecasting, what's called nowcasting in a very short term, they look at all kinds of data sources, including lightning, to issue warnings. And so the challenge here is to really further exploit the GLM optical lightning data set, which is a new data set, and it's very underexploited at this point. We know from past research that sudden increases in flash rate are indicative of the formation of potential severe weather effects. So this is known as a lightning jump. And so what we're wondering here with this challenge is, can we generalize the lightning jump, which is sort of this one-dimensional time series of flash rate for a cell, to higher dimensions by exploiting all the different dimensions of the patterns in the lightning data, whether it be area, energy, the particular rhythms of little blips of light within each flash. There's all these signals that we can use to try to elicit new and better warning data. So better warnings save lives. That's why we're doing. That's why the question is pressing. And we need better warnings that are more timely, giving people time to prepare, and more accurate, so you have fewer false alarms and less sort of desensitization. People not caring so much when the tornado sirens go off because, oh, they went off last week and nothing happened. So what does AI bring to this? Machine learning methods bring the ability to find and understand undiscovered patterns in the lightning data, sort of a generalized jump signature, if you will. And we are able to let machine learning lead the way towards physical discovery of some of the underlying storm physics. So there's really an opportunity to get some new scientific knowledge out of this approach. Other than that, I think I'll just yield the rest of my time. I think we're really looking forward to doing this challenge, and it's a really exciting time to take advantage of the geostationary lightning mapper data.
Excellent. Thanks so much, Clem. Perhaps time for one question.
Hi, do we just go ahead and ask? Can I
Yeah,
ask?
jump in, yeah.
I was gonna type, but I figured that'd take me longer. I was wondering if you're planning on constraining your projects to further challenge to a specific, I guess, mid-latitude area. Is there a constraint also for seasons? And you mentioned several different hazards like hail and tornadoes, which makes me think about mid-latitudes, but I was also wondering if you're thinking about some other severe hazards.
That's a great question, and really the domain we're going to be looking at is the full disk of the Earth. The GOES weather satellites are in geosynchronous orbit. They have a view of almost the entire face of the Earth. So, the training data for this would likely include warning data, historical warnings issued by the Weather Service, and those obviously are concentrated in the United States. And so, many of the highest severe weather effects occur in what's known as Tornado Alley, for example. So that, there's some time periods and geographical areas that we could focus on specifically in order to work this challenge.
Excellent, thank you. Clem, there's a question from Catherine Rays, and I might just, if you don't mind, Catherine, I might just read it out. In getting the optical lightning data set, do you also look at cloud clusters or positioning of other weather features as well?
Absolutely. GLM, the lightning mapper, is co-located on the weather satellite with the advanced baseline imager. This is the premier multispectral weather imaging camera. And so they're being co-located on the same platform gives you an incredible advantage towards getting multispectral background data of what's going on with the clouds, even at night, because you can use the infrared emissive bands.
Excellent, thank you. All right, Clem, I think you're off the hook, and why don't we change gears, and Rahul, even if you're standing by. Rahul's from Marshall Space Flight Center, and I know you have some slides. I can click these through for you if you'd like.
Super, thanks. So a slightly different challenge, maybe a little bit from data systems perspective, but a really interesting one. And it has cross-cutting applications within Earth science, not only for research, but for applications in environmental monitoring. Most of you may not know that NASA hosts the largest archive of Earth observations, and it's growing like steadily. We have about 30 petabytes. It's going to grow up to 250 petabytes within a few years with new missions that we keep launching. So the primary objective of this challenge is to build a knowledge discovery framework that would allow people to explore our archive to find unusual patterns and events. Can you move to the next slide? So as I mentioned, it's to enable users to explore our archive. We'd like to constrain this challenge to a query by example approach, where a user can specify an example of something interesting they're looking for. And the framework that is developed as part of this challenge can find that in the archive and find where it's occurring in different space and previous time locations. So there are some additional requirements that are added here so that it's not as, people don't treat it like a straight classification problem. The methodology needs to work, needs to be general purpose and work on variety of events and patterns. I'll give some examples of these. They need to work on images from multiple types of instruments. We can constrain it down to certain instruments that have similar spectral characteristics like MODIS and VIIRS. The methodology must also discover events that are at different spatial scales and resolutions. And this is very important because we want this to be a general purpose algorithm. There is a design component to this challenge that, there is a retrieval aspect of it also. So it has to be designed in a manner that it can find similar images in really optimal manner. The goal here is if the challenge is, the result is good enough, then we can actually incorporate it into our testbed operational system. So the key science driver here is that, new science, new research often starts with observing something interesting in a data set. And a canonical example here is from the first NASA weather satellite that was launched in 1960. Where they discovered these cloud plumes that were later attributed to smoke from ships that led to the role of aerosols and the impact of aerosols on the radiation budget for the Earth. So this is how, something interesting can lead to a completely new scientific area of research. Next slide, please. There are obviously cross-domain benefits for having a framework like this. This could be, just for applications such as disaster response or for monitoring environmental changes. Some specific examples is looking at severe things related to severe weather, whether it's tornado or hail damaged tracks, trying to identify MCSs within the data. For environmental monitoring, it could be looking at icebergs that break off. So there are different applications that this framework could enable. And the other key point here is it would address a key gap that exists in our existing search and discovery tool, which are pretty much based on keywords. This would allow people to explore our archive based on actual imagery. Next slide. We do have the data available. There is a service-based API that would make available to the participants that they can access a lot of the imagery. And we have about 20 years worth of imagery that we can pull out and utilize for this particular challenge. Well, let me know if you have any questions or if you need any clarifications here.
Anyone got any thoughts on this one?
Rahul, hello, this is Ivan. A quick question. I was thinking if a kind of graph database with some NLP techniques could be useful to this kind of challenge. I mean, it is the kind of right way to kind of frame this problem. It is I mean that's this starting point of this kind of challenge. Could it be?
The challenge here is you're saying graph database with NLP.
I mean, sort of. I mean, like and it's first point to then move kind of forward.
I was envisioning this more as a image-based search query by example approach where you could use something within deep learning approaches to find.
I'd like to know if there's any machine learning folks on the call who, as you were hearing Rahul's description, where your heads went. Has anyone got some initial hunches on, like Ivan, methods that could be useful? I know there's some heavy hitters on the call. Yeah, go.
Greg, there was some approach merging computer vision and natural language working on knowledge discovery. You've got some startup from like embeddings Poincaré from Facebook, completely open source. You've got the papers and Git project. Can be really useful, extracting entities and try to recreate ontologies based on that to make some search. Raoul, if you want, we can exchange on it at any time. I'm in the Bay Area.
Great stuff. Thanks, Greg. All right, please keep the conversation going in the chat, and hopefully Rahul can stay for a little bit longer. I'm going to suggest we change gear and invite Brandon from MIT to take us through the Earth Intelligence Engine.
Thanks. Hey, everyone. I actually want to start with a quick story. Are there other slides for this one? If you go forward one. Okay, great. Yeah, I would love to start there. So just a quick story. Last year, in spring of 2019, an Air Force base called Offutt Air Force Base got really badly flooded. And this was an interesting case because in 2011, there was a small flood that gave warning. And then in 2015, there was actually a report on this Air Force base that acknowledged the flooding risk. And to be clear, Offutt Air Force Base was not just some random, unimportant Air Force base. I don't know if such things exist. But Offutt Air Force Base was actually the headquarters of U.S. Strategic Command, which is responsible for, among other things, nuclear strategic deterrence. And so the fact that despite all of these warnings, both in the years and in the days ahead of this massive flood that caused $400 million of damage, they had so much evidence that it was coming, yet they didn't act. And it caused $400 million of damage. And the question is why? And part of the problem is that weather and climate data are really complex. Lots of tables, lots of graphs, but our goal is to really simplify the process of turning data from weather and climate and Earth observation data into usable, actionable insights. And so the Earth Intelligence Engine is the project that's framed around that mission. If I can go to the next slide. For FDL, we're looking specifically at 1/3 of the Earth Intelligence Engine, and that's the visual models. I don't know what happened to the slide here, but at the top it says, we will simulate satellite imagery given future climate conditions. And so the idea is, given an input satellite image and a climate model that projects, that has a climate projection for that location, what does that place actually look like given the projected climate in 10 years, 20 years, 30 years, and so on? And so our proposed approach, although this is flexible, is taking that input image, segmenting it into a segmentation map, using that climate model or that climate projection to somehow alter the segmentation. That's probably going to be the hardest part. And then transferring that segmentation map back into a satellite image. So I'll leave it open for questions, but that's the Earth Intelligence Engine, and really looking forward to working with people.
That's really exciting when you talk about simulating satellite imagery. I've been exploring that for a project at Planet. And so I'm wondering if you already have kind of an Earth simulator that you might be using, because I'd love to talk to you about that. And then a little crazily, I've been wondering if we can actually take a flight simulator, which already draws the Earth, turn the camera looking down. Now you have synthetic remote sensing imagery, like taking the Microsoft 2020 flight simulator and using that for synthetic data.
So that's interesting. We've definitely not thought of that. As far as simulating Earth, so far we've been using GANs, generative adversarial networks. And we have, we've simulated coastal satellite-like images But there's definitely a lot of possible ways to do this.
No, that's really interesting. Certainly training generative models that can sort of represent your sort of latent distribution is also an interesting direction. GANs are somewhat known to suffer from diversity problems. So they can be very good at a particular narrow niche. But that's also interesting. So yeah, I'd love to chat with you.
Great.
Remote sensing data is very expensive and tedious to label. And it's naturally error prone. So simulations is a really interesting direction.
Yeah.
Hello, this is Diego. It's also interesting because I also wonder what is the effect of the particular climate model that is going to be used in correlation with the images. Because of course there will be some noise coming from not reproducing the fake image to make it real, but that would be basically a source of uncertainty in itself. And then on top of it, what's the influence of the particular model that is added on top?
That's a great question. And we've been focused more on the satellite image segmentation part so far. So I honestly don't know. I have no idea what the impact of the climate model will be. We're certainly looking for, I think we're looking for people on our team who have more experience on the climate side, because we're a couple of computer scientists and we really have no business doing this. No, just kidding. But yeah, we haven't tried.
I'm not a climate scientist. I'm not a climate scientist.
That's why we're interdisciplinary. Don't worry, Brandon.
That's right. That's right.
Excellent. All right. Well, in the interest of time, I might suggest we jump forward. Thank you so much for that.
Thanks, James.
And our next Earth Science is Where Droughts Are Born. And I'd like to invite Jonathan Stock to take the mic.
Thank you, James. Hi, folks. My name is John Stock. I run the National Innovation Center for the U.S. Geological Survey. The USGS is a science agency in the U.S. that's in charge of essentially mapping where water is, monitoring water, mapping earthquakes, volcanoes, all kinds of fun stuff. What I'd like to do with you guys is talk about the challenge that's in the title here, Where Droughts Are Born, talk about what I see as the opportunity, describe some of the data that we would work with, and then describe the folks that you'd be working with. So with that, let me start. Imagine that you could sit above, maybe back a slide there, thanks. Imagine that you could sit above and look down on Earth's surface and watch all the streams in real time. And imagine as a drought comes on, as rainfall stops and you start to evaporate your moisture, that stream network cracks, right? That would be your leading indicator for all the ecosystem effects that will follow on from that lack of water flowing in the streams. The streams represent essentially where the groundwater table intersects. And so by mapping in time series as the streams would track, you're essentially forecasting where the ecosystem drought is headed. So that looks, how's James, am I, is the video and audio stable? I just got a warning.
You're good enough, it's okay.
Okay, so that's the challenge. We'd love to be able to do that. But right now, what would it take? It would take an army of folks who could sit down with daily imagery for a country and then map out where all the water is. And we know we'd never be able to do that, right? And so that's, of course, where this unique combination of AI plus high performance computing plus daily or weekly satellite imagery comes into play, because for the first time, we actually have the possibility of doing a problem that's challenged us for a very, very long time. So that's the challenge. The opportunity then would be to essentially hit a button and see where a nation's streams are, where all the flowing water is at any time. And the impact on that would be, heads up on what's coming at you in terms of water supplies and drought, as well as all the ecosystem impacts. So the data that we are going to deploy for that will be a series of satellite imagery. It's probably somewhere in the 1 to 5 meter resolution. We're agnostic about whether it's going to be optical or other sources. That's a discussion we're having. What the USGS folks will do is begin to create the training data sets for a series of places in the US so that we have a time series showing where the water is in the streams. And then the team here will work with a group of folks from our water mission area across the nation, from our national geospatial group who are using high resolution topography to find streams, and from our national land imaging group who are our imaging experts. And again, the goal is to see if we can create this almost real-time awareness of where streams are on Earth's surface, using it as a tool to then forecast oncoming ecosystem drought. So that's the brief discussion, and I'll leave it open for any questions.
Yeah, I've had a question about what's the satellite resolution that you need. So planet imagery is naturally 3 to 5 meters, mostly sort of RGB with some near infrared. What's the resolution that you need?
So I think we're adaptable on the question. The better the resolution, the farther up the branching network you can go. So the kind of streams we'd like to be able to capture are 2 to 5 meter wide, very small streams, because that's where you see the signal earliest. That's where the droughts are born. However, we recognize that we're essentially pioneering a concept, and so we're willing to work with coarser resolution data if we can show the concept.
See, what's nice about the planet?
Brad, did that answer the question?
No, that's great. That's great. So the planet imagery somewhat trades off resolution for an increased cadence and global coverage, right? So does an increased cadence help your problem? So is there the time component?
However, I think the flex points for us are on both resolution and cadence, right? Because ultimately we know we're not going to solve this problem in one go.
Right.
Hey, Jonathan and Brad, I guess. This is Andrew Annex. I was a participant on the FLEX team last year. And we had like a lot of hard fought won knowledge from that. And one thing that sort of exists already, there is this like algorithm that segments river widths like from Landsat imagery, and be interesting to that's one of the ideas we had would be to apply that to the planet data, so you would get these river width estimates, increased cadence, and also at smaller streams where we can take advantage of the higher spatial resolution. If there are any SAR data sets, some of those are coming online with the increased spatial resolution on the ground. That sort of feeds into that question. So you could just start from the existing data set, the sort of the broad like Landsat scale resolutions, or sort of focus in on improving estimates where you can't see those rivers right in Landsat, but you might be able to see them in Planet.
Right, that makes sense. Hi, Andrew. Good to
hey, how's it go?
Yeah. Did y'all end up your team last year? Did you end up using methods like NDWI, some of these metrics of detecting water, or were they not,
the European team ran into this, right? And it became this big question where how can neural networks really improve much on the ground truth? Because a lot of the ground truth in itself was generated using those thresholding values. So it became the sort of circular question of like, would it be worth training on like the Copernicus flood extent data, for example, and if that's actually useful or not. So that's why that project went into slightly different directions from using visual data for anything. But there are still a lot of really interesting sort of problems we developed like while researching all this. And one of those was like getting these river widths using the higher resolution data. We didn't end up doing that, but it should be tractable because the algorithms are out there and they use just the RGB values, right? Like I don't think it's anything too specialized, but I am also aware that some of the newer Planet satellites will probably, like the Super Doves, I would imagine, are probably more tuned to do NVDI. Is that correct, Brad? Or the
I don't.
index?
I'm fairly new to Planet. I don't know what I can or can't necessarily say.
Yeah.
I don't know like what is or internal knowledge, but yeah, the super doves, folks have talked about those. I think I'd love to understand the forecasting aspect. So assuming you've segmented out some creeks and rivers, you want to forecast something, right? You want to regress something, like what's a threat or what's a drought?
Well,
What's
river width would be one thing. You're trying to infer basically how much water is in that scene, right?
Now, hang on, Andrew. The forecast element, and James is probably going to cut us off shortly.
Yeah, he is.
Well, luckily, some of us are also
the forecast element is that the rivers are leading indicators of what will happen on the hill slopes and the soil profiles. So if you can watch the rivers disappear, the streams disappear, you know that you've got ecosystem drought coming into the soil country where all your vegetation is.
Yes, I agree with that.
Excellent, thank you. I am gonna, as chair, jump in. I'm just completely thrilled that there's a good kind of conversation going, but again, sort of conscious of folks on the call who may be wanting to talk astrophysics, because that's next, and we're tracking pretty well for time, but we have 3 more to go, and we have approximately 25 minutes left. So Jeff, do you want to take the helm and take us through Star Check?
Hello everyone, my name is Jeff Smith. I work at the SETI Institute and at NASA Ames Research Center, and I have been involved with the Kepler and test missions for a long time now. And so this particular challenge is involved with using the test data set to find interesting stars and star systems in our local part of the galaxy. So the next slide, please. Okay, so you're probably familiar with the Kepler mission. It's been a resounding success. It's found thousands of exosolar planets in our galaxy. We now know that planets are everywhere, not just that, but Earth-like planets are everywhere. TESS, the Transiting Exoplanet Survey Satellite, is a follow-up mission to Kepler. And this one is basically trying to do an all-sky survey, but looking for planets, primarily looking for planets that are much further in, much easier to do follow-up analysis. Now, we did have a 2018 Exoplanet Challenge in FDL. That was involved with taking data that was manually vetted and then using supervised classification in order to try to develop a classifier. What I'm interested in doing here is going beyond simply supervised classification, but see what else we can do with this data set. So we have the test data, which has been collecting data for almost 2 years now. We're almost at the end of the 2-year primary mission, and we're going to have certainly at least another 2 years of a extended mission and probably more after that. There's a lot in this data that we haven't looked at yet, and we haven't fully unleashed the power of modern machine learning techniques to just look at everything that's in here. We have basically 2 different types of data. There's this 2-minute target data that looks at a smaller number, about 16,000 targets per sector or month, and that's at a 2-minute cadence. But we also have these full frame images, which is every half hour we take a image of a huge chunk of the sky. And we're doing this every half hour so you can see a time series of how a huge chunk of the sky is evolving. This data set has not been exploited much yet. I'm part of the pipeline that develops the data processing pipeline for TESS, and we are currently trying to create time series out of this FFI data, which we're currently processing, and more will be available this summer. So there's a lot there that just hasn't been seen yet. Now, what specifically we search for in this data, I want to leave that open to some extent to see what the participants are interested in. There's a lot of things we can look at. For example, we can continue looking for planets. Instead of using the traditional matched filter methods that we use for search for planets, maybe we can use some more modern machine learning techniques to actually find the planet signals. Maybe we can find single transits instead of looking for periodic transits, which maybe will allow us to find more longer period planetary signals, which aren't so close into the host star. So basically, maybe we can find things that we're currently missing. But there's other things we can look for. You have occulting orbital material. So you have stars that are these protoplanetary systems. We have a bunch of debris and dust that's orbiting a star. And we've seen examples of this before in the data. Maybe we can search specifically for these protoplanetary disk systems and have a better understanding of how planetary systems evolve and how likely it is that habitable planets might evolve. Third thing is looking at the stars themselves. We could look at unusual stellar behavior. Many people may have heard of Boyon's star, which is basically this star that periodically has this huge drop in total amount of light coming from it. Some people said it might be alien megastructures. Might be, but it also might be decaying comets or something else. There's certainly other cases of that. Maybe we could create some type of anomaly detector looking at the TESS FFI data that searches for just weird behavior and may signify weird stellar objects that we just haven't seen before. So there's a lot to explore here. We know a lot about the data, and I can certainly help a lot in conditioning and interpreting this data, but there's a lot of different things we can explore, and we need help exploring this data set. So thank you very much. I'm happy to answer any questions.
Thanks so much, Jeff.
Can I make a quick comment?
Yeah.
So we had a project last 2 years ago on like looking at the systematic noise, trying to model systematic noise for tests as part of the pre-processing step. So we actually played with some simulated test data before it was launched, as well as Kepler data. And one of the things I've been meaning to do is basically look at unsupervised machine learning techniques, or like stuff looking at anomaly detection, which is basically looking for everything which doesn't look like stuff that we've seen before. Like we've been playing like and looking at like the dips that we get from exoplanets going in front of the sun, but basically throwing away everything which doesn't map to one of these things that we expect to see. And I have been curious to know whether it makes sense to look opposite, actually looking for anomalies compared to what most of the data looks like.
Yes, that's one of the key things I would be interested in looking at here. I mean, when we're doing our traditional planet search, we're looking for a periodic signal and a very distinct transit signal shape. And these match filters that we developed is very good at looking at things like that, but it's not good at looking at anomalies. It's not good at looking for things that we don't expect to see. And it's very true, there's a lot of systematic instrumental noise in this data set. And we've developed a lot of methods to identify and remove the systematic noise. It might be possible that we could develop some machine learning model that can just identify what is typical, what is systematic, and then identify what might be weird or odd, and look for that. And that's an indication of something that we're actually interested in.
So that's go ahead.
Hi, this is Lucianne Walkowicz. Jeff, I hope you don't mind if I jump in. Just to let you know, so myself and my student Daniel Giles have done exactly that in a machine learning approach to Kepler data. And we've been talking with Jeff and Anne-Marie Cote, of course, about this particular project, which I think would be really exciting to see FDL work on. But yeah, applying like basically a K nearest neighbors approach to identifying outliers and also scoring them.
Oh, so like I was thinking using more like modern machine learning tools, like trying to actually build. So like what Jeff mentioned just at the end now. So that's basically what we started doing in the project a few years ago, trying to model the noise processes, the systematic noise itself. And using that, we can actually we can look at low probability events, which are not likely to be from the noise processes.
Yeah, I think that would be very helpful also with respect to stellar flare identification. So a lot of the work that is going on there would really benefit from a better understanding of the noise.
Yeah.
Oh, I just wanted to mention too, Brad Newberg. I'm wondering if anything from the biology literature in terms of deep learning can be used for rare diseases or drug discovery. A lot of times they're dealing with kind of rare events or anomaly detection, and they're trying to use deep learning. I've been leaning a lot on the biosegmentation literature, for example, for some of my own work. So there might be answers in adjacent literature, but they don't call it, your exact problem domain.
Excellent.
But I think what's also interesting, I think, is not only because we might think about something that is unusual, but is very common out there, just that we haven't seen it yet. So from the point of view of the light curve, it would be really interesting to observe how the light curve builds on with time, and whether we can use machine learning for an early detection of different kinds of objects with time. So I'm thinking about things similar to how we approach supernovae light curve, that they have characteristic features. And so some similar approach can be possibly automated as well using machine learning.
Yeah, I agree with what everybody's saying. Just one thing to mention is that we can either do this at the light curve level or the pixel level. I mean, we develop light curves for individual stellar objects. It may be possible to do things at the pixel level. It's much more of a challenge, but in principle, there's more information there because by keeping the pixels separate instead of combining it, you keep an spatial understanding of what's going on local and around the star. So just something to keep in mind. We don't necessarily have to do time series. We could do pixel time series, not light curves time series. Okay. But again, the latter is more difficult.
Again, thank you so much for all the good thinking on this, and it's great to see the conversation already starting to have some momentum. Andres, I was wondering if I could give you the mic and take us through the other astrophysics challenge.
Yes, James, thank you. This is Andres Muñoz Jaramillo. I am part of the Southwest Research Institute, and I have led FDL challenges on the last 3 years on heliophysics. But the sun is also a star, and there is a very strong connection between what is happening to our own personal star and what is happening out there. And so this is a project that is a sister project to the one that just was mentioned before, but with a focus on stellar magnetism. So the majority of our exoplanets that we have detected are very close to our stars, to their host stars. And these stars are cooler, and so we say, well, there is liquid water on their surface, so they're in a habitable zone. But the truth is that the magnetism of a star can significantly affect whether a planet is habitable or not. Just staying in our solar system, we know that the main reason why Mars has such a thin atmosphere is because it has been stripped away by the solar wind. And Mars is a planet that is significantly farther away from our star than a lot of these exoplanets. And so to understand habitability, we not only need to understand whether the planet is warm enough, but also what kind of interaction does it have magnetically with its host star. And so if we move to the next slide, please. Yeah. So here I have two images. One is of a planetary transit on the left. So what you're looking at here, those dots are the brightness of the star. And as the planet crosses over the surface of the star, then the brightness of the star drops. And then when it crosses on the other side, it rises again. Now in the middle, you have this blip. And it's an interesting blip because this happens when the star has a spot, a dark spot, and the planet crosses over it. And so you have, you see this relative brightness. So we know that the stars have planets, and we know that the stars have spots. Now, if we look on the right, you have the sun as a similar curve for our sun, just with the spot. So you have a brightness of the sun, and then the brightness drop when the spot crosses, and then it rises again once the spot goes outside of the disk, rotates outside of your field of view. So the idea is that for centuries now, we have been understanding and studying how the solar magnetic cycle works just by looking at spots, at dark spots. And the question here is that taking advantage of these beautiful stellar databases, can we create something akin to the data sets that we have been using to study solar magnetism for centuries now? And that is the core of this project. So I'm going to tell you something like a little story that I think blows my mind every time that I think about this. the solar cycle. So the sun has a solar magnetic cycle. Sometimes has lots of spots and lots of magnetic activity. Sometimes has very little. This is the single most important driver of variability in the solar system. And the person that discovered the solar cycle was a German astronomer called Heinrich Schwabe. He made drawings of the sun almost daily for about 40 years, 200 years ago. He started in 1826. About halfway inside his survey, he realized that the amount of spots increased and decreased with time. And he published a letter saying, hey, maybe there is a cycle in the sun. The thing that is fascinating here is that a lot of the time, stellar spots and their crossings are an obstacle for our detection of exoplanets, right? So it's noise. We want to get rid of that so we can really identify the crossing and say there is a candidate. Actually, Heinrich Schwabe's survey was exactly the same. The reason why he started drawing sunspots every day for 40 years was because he wanted to see if there was a planet inside the orbit of Mercury. So he was a planet hunter. He was not a heliophysicist. He was not trying to understand the magnetism of the star or anything. He was hunting for planets. And he was keeping track of these drawings because the sunspots were the noise, as the stellar spots are the noise for modern astronomers. But he made a fundamental discovery that has changed the way we understand the star that we live with. So what we're trying to do here is the same thing. We have hundreds of thousands of observations in TESS and in Kepler, and we can potentially radically transform the way we understand solar magnetism, stellar magnetism, by trying to understand and measure and characterize the spots that cross the surface of stars. So that's the idea in this project.
Thank you so much, Andres. Perhaps time for one question, and then we'll.
I have a quick comment.
Yeah.
So I know that parts of that is solved. It might not be published yet. Did you read Brett Morris' work and the people from UW? So he basically has a pipeline that finds all spot crossings in Kepler and TESS. So at least that part is solved. And there are a couple of other groups working on that. Just a comment.
Yeah, I know, maybe it's not published yet.
Yeah, perhaps let's take this one offline. I really want to give any researchers who might have a question the chance to ask a question of Andres. We have one more challenge in 12 minutes. So again, if you have questions, please use the chat channel. And if no one wants to jump in, I might let's go ahead and give John the mic, and you can take us through astronaut health.
Sounds good. Thank you, James. So, hi everyone. My name is John Kalantari. I'm a machine learning AI scientist at the Mayo Clinic in the United States. I'm also an assistant professor in the Center for Individualized Medicine Microbiome Program. So I'm the domain lead for the challenge project proposal called Long Duration Missions in Cancer, a test bed for building causal inference methods. So the motivation behind this project is that there's a lot of uncertainty associated with spaceflight, specifically health-related uncertainties that could potentially impede the success of future missions or impair the decision-making of our astronauts. And one of the many uncertainties associated with spaceflight is the initiation and progression of cancer. So molecular alterations are pretty ubiquitous in spaceflight, and they magnify the risk of cancer mortality and morbidity in long-term missions. An example of this that many are familiar with is radiation exposure from solar particle events. But this is only one of many possible causal drivers of cancer that can present a significant health concern for astronauts during interplanetary and Martian surface missions. Now, by understanding the molecular basis of cancer development, we can better assess the impact of various risk factors on astronaut health and either treat or, better yet, prevent cancer before it arises. The problem is, though, that traditional predictive models only get us so far in allowing us to model what has been seen in our observed data. And in order to generalize beyond our data, we need to account for what I refer to as the known unknowns of cancer biology and spaceflight. And to do that, we need to start building new methods of causal reasoning that underlie our predictive models. So to date, we've developed a new Bayesian inverse reinforcement learning algorithm called Pure IRL. And at the Mayo Clinic, we've tested and validated the algorithm in inferring the evolutionary trajectory of colorectal cancer based on genetic mutation data derived from a cohort of colorectal cancer patients. And so we're seeking to scale this algorithm across a larger patient cohort, as well as incorporate additional multi-omic data sets. And what that means is, in addition to whole genome sequencing data from our patient tumors, we're including epigenetic methylation data and microbial 16S data. So the goal for the FDL 2020 astronaut health team is to incorporate methods such as from active learning and distributed reinforcement learning so that we can build a more scalable and comprehensive model of cancer progression that's based on causal biological mechanisms and not just correlations. If we have an AI framework for constructing these types of holistic models of cancer from our patient data, that means that we have a personalized screening and prediction platform for each astronaut's long-term health. The platform will allow us to begin to ask questions, perform simulations that replicate conditions that we know exist in space, like the presence of radiation exposure, microgravity, and the impact of diet on gut health. If we know that, then we can forecast how different perturbations or interventions like new drugs will enhance or inhibit disease progression. And so with that, for the sake of time, I can answer questions offline too.
Thanks, John.
Quick question.
Sure.
So, like, first of all, the project definition, I think, like, looks good, especially like the iterations over time. The scope is very, very, very broad. So it's basically what many researchers across the world is trying to do. Do you have any like concrete way of looking at what it should, like, what would be a good outcome?
Yeah, so the way that so the status quo is, the gold standard is the randomized control trial. We cannot beat that. The way that we're validating these approximations of causality that our algorithm is outputting is by looking at both the literature, but also Mayo Clinic is the #1 hospital in the US. So we have the expertise to basically validate what the algorithm believes is causing, rather than just correlating different factors together. So for our initial preliminary data, we were able to validate the established canonical model of colorectal cancer that's in the literature. So this, what we're asking for the team for the 8-week challenge is, can you integrate multidimensional data beyond genetics? If you can do that, is there a way to incorporate human expertise feedback in the learning process, as opposed to a priori having a human specify what is known at the beginning?
Cool, thanks.
Yep.
Excellent. There are a couple more in the chat. There's one from Afshin. I don't know if you want to say that to everybody.
Yeah, no, absolutely. Microbiome data from the ISS would be huge. For the sake of the 8-week time frame, we're looking at data that we have already in-house that we're processing and generating into a format that the team in July can just start running with. That is microbial data from our patient tumors, methylation data from the hosts, and the genetics. The idea would be, if we can, as a proof of concept, demonstrate that we have an algorithm that can integrate those different omic data sets, then we can scale it, then we can start to incorporate these additional data sets. That would be huge. Yeah, the ISS environment data, that would, oh my gosh, that would help build that more comprehensive, holistic model.
Great stuff. All right, well, thanks so much, John, and we have 5 minutes more of our allotted time. I just wanted to wrap up by saying that obviously we're still very keen for researchers, particularly researchers that are interested in the challenges that we covered today. I wanted to thank so much our faculty for taking the time. Of course, there's a lot of prep, even presenting for 5 minutes, and I really appreciate you taking the time to join us today to share these challenges. As a reminder, please, if you're interested, you can apply at frontierdevelopmentlab.org or fdl.ai if you want a shortcut. And then also please let anybody that you think that you may know who would be interested in these challenges. Of course, we'd love to have them apply. So I think that's pretty much our show for this evening. I just wanted to thank again our partners and the team at the SETI Institute and our Trillium team as well for all the preparation that goes on behind the scenes to make this happen. And looking forward to the next time we get together. And with that, we'll wrap.
James,
yeah.
Another thought, as long as we've got everybody on board here still, one of the most powerful parts of our ecosystem are people like you who are on the call with us today. We're still, as James said, looking for more applicants as participants and mentors for these programs. So it would be great if you could all leverage your own personal networks within the science community and or AI ML communities, and let people know about Frontier Development Lab and the projects we hope to undertake this summer, and see if we can't, keep the momentum going on applications.
We just had a question from Lucia. How many participants are you looking to fill? I mean, each challenge has 4 researchers, and essentially the composition of a team is more or less 2 domain specialists, so people who really know the problem, and 2 machine learning specialists, so people who really know the solution. Although, these days, a lot of people are hybrids, and so sometimes we actually have a team which is composed of hybrids. But each challenge, essentially, we're looking for at least a few specialists who can really understand the science, and then machine learning people who can understand state of the art in terms of the pipeline. Well, I'm happy to stay on. I really realize we're at the top of our allotted time, but if people do want to have, if they have questions about the program and want to talk, we're happy to stay on a little bit longer. But also realize that we've just had everybody for 90 minutes, and I do appreciate that everyone's busy. So happy to call it a day, and then we'll stay on here a little bit if you'd like to talk in a smaller group.
Thanks everyone for joining. James, I think you do have a couple of people who'd like to stay on and get some questions from you, so that's great.
Sure.
And I'm going to bow out for the next meeting, but wonderful to have everybody here today, and thanks especially to our presenters for your articulation of the challenges. We've got an amazing set of challenges. We hope to be able to do them all. We're still finalizing the pursuit of the funds from NASA, but things are looking optimistic to fully fund all the challenges we want. We'll keep everybody posted on the progress of that. But very, very exciting set of topics, and thank everybody for their hard work in putting these together.
Hi, Bill. Quick question. Is there a nice sort of landing site that describes the 2020 challenges and the role of the mentors that I can use to share internally on some forums to see if we can shake out some more mentors or something?
Yeah, we have a mentor briefing. I'll send you, Brad.
Is that at a URL that I can, or maybe something I can just attach in the Slack channel is what I'm thinking.
Oh,
internally.
Yeah, it'll be a Google Doc, but yeah, we can do that.
We got that, James. Have we updated the website yet with these draft challenges? That might be
the website. Yeah, the website has just a sort of thumbnail sketch of the challenge. We haven't got the longer description, but yeah, perhaps if you take a note of Zoe's email address, so Zoe at FDL.ai, and you like a longer description, we can send that to you.
Yeah, just some like collateral that I can post in internal Slack.
I'll follow up with you directly.
Okay, thanks, Zoe.
I think it'd be good to share that, so with the community that's on board here today, because if for those reaching out to colleagues and friends to describe what's going on, it'd be good for them to have something to share, like Brad is looking for.
Yeah, and the reason we don't share them sort of far and wide is that they're still sort of in evolution. But certainly, I mean, for the purposes of getting people interested, we can share them with you.
James, I have a question about time zone. People from Europe who were interested in applying to US-based challenges.
Yeah, so we're going to adhere to a working day. So we're going to encourage the teams to FDL is remunerated. You are essentially employees of the SET Institute. So we'll have a working day, and we're going to temporally locate the working day on the eastern seaboard. So for the people on the west coast of the United States, you'll have to get up a little earlier, and for people in Europe, you'll be essentially starting midday for you. But certainly the idea is that we can have a working day where everybody's in lockstep, and as I said, that'll be on East Coast time.
We also had, James, a question about when people would hear back about the people who have submitted applications.
Yeah, so we try and get letters out to you, acceptance letters, in early May. I think we're loosely tracking on that. We've actually done a lot of work already. We really respect and sort of want to sort of get you a clear understanding of how your summer's looking as soon as possible. I'd say that certainly by the second week of May, you'll know from us. It takes us a while to put the teams together. As mentioned, our sort of method is a bit like the way that Hollywood does a movie. We get the challenge definition, we get a faculty, and then we start choosing the right team to crack the problem. And that essentially starts as soon as the closing date of the applications wraps, which is next week. And that gives us approximately 3 weeks to get all the teams together and get the announcement letters out. So yeah, certainly first week of May would be what we're aiming for.
So James, I have just one question on this.
Yeah.
If that's okay. So for some of us, of course, a month full of the time that is required to build up all the teams and so on. Some of us also need to communicate to their workplaces some in advance so that they can take time to take the program. So would there be any help on this from this point of view, so that some people that may be accepted be notified in advance so that they can let their employee know in advance?
I think we're happy to work with you, and I think if that's an issue for you, please do reach out, and we'll do it on a case by case. I think I mean, generally, what happens is that if you've assigned the challenge you want to work on, that generally we know pretty early whether you'll be right or wrong for that challenge. But in some instances, there's other challenges that we might invite you to work on. And we do actually have more challenges with our colleagues in FDL Europe, which is a completely separate program supported by ESA. And it may be the issue, if you don't get for your first choice, that there's invitation to work on one of the ESA challenges. So yes, we'll if it is urgent, of course we'll try and work with you on that.
Mm-hmm.
Just reach out to Zoe.
Yeah, okay. I'll send an email then so to ask better. Okay, thank you very much.
There's a question about interviews. Yes, we interview everybody. It's not just based on CV. Once you apply, there's a process where we'll get you on and you'll talk to Armine at the SETI Institute, and then there'll be a follow-up as well, just as we sort of get to the teams, get more confidence about how the teams are looking, and we'll do a technical interview as well. So yeah, it's not just based on resumes.
And James, we had a couple questions about number of total participants and team size. So just wanted to reiterate that both, I believe for both Europe and the US, team sizes will be expected to be 4 people, not, there was a question if 6 was the European team size.
No, all teams will be 4. And we're going to stick to the FDL formula, which is 2 domain specialists and 2 ML specialists.
And so we'll field a team of 4 for each of the challenges that ends up getting funded.
That's right, yeah.
For Freddie here, for mentors on the European side, UK side, do you, in the previous year, what we did is most of the time there was remote support. There was a 2-week on-site visit. For some people it was longer. Now that it's going to be purely remote, how do you reconcile the need for mentors versus the time zone gap?
You might have to, do you mind reframing that?
Yeah. Basically, I'm saying I was supporting 2 US teams last year, but I could visit them on site. So, if you're there for 2 weeks full time, then you make the best of the time. You can travel quite a lot. But now that this is going to be purely remote and the overlap is not going to be so big, do you obviously there's going to be an issue here. So are the mentors for the US teams going to be US based, or do you see some kind of compromise here?
Yeah, sorry, I lost lock on that. But yeah, the essentially, as I say, the US challenges will be temporally located on the East Coast. So if you're in Europe and I guess you're happy to have a working day that starts a little bit later, early afternoon, and then sort of goes into the evening. That's would be the expectation, and then we will for the Europe teams will kind of probably temporarily locate that on GMT, and so or BST, and so that'll be a normal working day for folks in Europe. But yeah, I think certainly if you're mentoring in the US, we'd probably need or ask you to work or change your clock, if you like, so you're working on US time.
Yeah, that's fine. That makes sense.
Hello. So sorry for butting in. I'm in India right now, and it's 12:30 or it's 12:40 now. So if we are all around the globe, how do we propose having this whole setup? Everybody working at the same time.
Yeah, it is really tricky for folks that aren't located in either the West or East Coast or Europe. And we might have to get back to you on that. Not a great answer. That obviously, if you're willing to sort of adjust your life to work in our time zones, then that's an option. But unfortunately, I don't think we can have asymmetric timing where there's a situation where you're, it's not like coding where teams can work on something and then it gets handed over. I think we need the teams to be actually having the same working day. So probably not a great answer, probably not the one you wanted, but happy to be flexible as we are with everybody who's got a unique situation, and see if we can find a solution.
So if I may, so if the teams or if people work individually for, let's say, 3 days, and every 3 days there is a common meeting or so where results are evaluated, so will that kind of a scheme work?
Unfortunately, yeah, Andres, please jump in. But my initial hunch is that you'll find that FDL work is so collaborative. It's very hard for there to be a sort of handover like you just described. But Andres, do you want to?
No, I just wanted to say that this is something that we have never done in the FDL yet either. So there is a lot of this process is not complete on the design of how the workflow will work and what kinds of any space. I think it also will at some point depend on the expert. There's going to be some flexibility, and the leaders of the teams are probably going to have to make choices depending largely on the expertise of the participants that are involved. So this is not going to be, I don't think in this moment we don't have like a blanket protocol that every team will follow. And so yes, I agree with James, most likely this will be a factor. Where it wasn't before, it will be a factor where people will consider if there are two people with the same expertise, but some of them are in the same time zone and some are not. These kind of choices will be made. But yeah, I think that in this moment, this is something so new that there is not yet like a standard.
And I would just encourage anyone who's thinking about it, the only way that you'll even get into consideration is by applying. So if you have an inclination, apply, and we will evaluate each and every application carefully.
Thank you very much.
Thank you.
I'm wondering, are there any other projects that have done fully remote research sprints that might have ideas that we can borrow from or advice? I'm not aware of any, but maybe in the network.
The successful one we looked at was actually the Hyperloop. But yeah,
nice.
we're definitely trying to look for best practice, and we're starting to get a pretty strong point of view about how we get that cohesion. But so much of it's about team unity, and there's this concept of presenteeism, and we think that we need to have teams that are working on the same working day just to create those really strong interpersonal dynamics.
Yeah, gotcha.
One question, what is it that you're looking in an application? For example, when you see the CV and then in the interview, but mostly on the CV, what are the skills that you are looking for? Are you looking for publications? Or what are the sort of things that catch your eye?
That's a really great question. We don't expect you to be published. Certainly, like a lot of our researchers are still doing their PhD or late stage PhD. I think strong coding skills is always something which we like to see. We also have people who have industry experience that actually equates for a lot, because industry provides sort of practical problem solving skills. Any other thoughts? Anything I've missed?
Yes, I would like to add to that. As someone that has worked with 3 different teams and has been part of the program for 3 years, I believe that also social sensitivity is critical. So participants that are sensitive to and are able to kind of understand and put themselves in the shoes of their team members, and that are generous with the. This is the FDL is an evolving process, but typically the participants are always very good, and where we always have the biggest challenges are interpersonal, not in terms of
from a CV.
No, but in the interview we will also ask you about this.
Yeah, we have a multi-round interview process. It really is, you know, it's very robust, and people get a chance to really kind of share their experiences in more depth if they make it to the interview rounds.
Right, you narrow down, I guess you may have like about 100 applicants, and you may interview, what, 20, 30?
No, we have, essentially we have a 5% acceptance rate. So this year it's might be a little bit lower just because of the health situation, but generally we have hundreds of applicants.
Mm-hmm. Thank you.
But don't let that put you off. And I think Andre's point about, you know, the ability to work in a team and being really sensitive to what it takes to do, you know, genuine research. And this is, you know, really looking at hard problems that no one's ever, you know, got their arms around before. You know, if you like, the hygiene factors, the collaboration hygiene is going to be particularly necessary as we work digitally. And so we'll be looking for those things very closely.
I have a quick question.
Yeah.
So I was wondering, are you looking to publish in the 8-week timeline, or is this something?
Oh, excellent question. No, we don't expect published results, sorry, documentation in 8 weeks. Essentially, you crack the problem, you get a pipeline that's plausible, you get some results, and you get if you like, we ask you to do a presentation, which essentially is if you like, the outlines of your published work. And then generally the teams keep on working, and we actually keep the compute availability working as well. And they're essentially the teams either complete by the NeurIPS deadline, or they complete by the AGU deadline. But actually some teams are still working even from last year. But certainly there's no expectation that you need to get a published paper in the 8 weeks. So yeah, thanks so much for asking. I should have made that clear at the beginning.
Also about computing resources, you know, since it's going to be remote, do you guys have any concrete plans about that?
Yeah, the FDL historically, or certainly for the last 4 years, has been in the cloud, and resources are provided by our AI partners. And generally, what happens is that different partners are like the champions of different challenges. And so we're not sure exactly how it's going to fall for 2020. But certainly all of the compute will be done on cloud technology.
Thank you.
I think we're winding down on questions in the chat, at least. James, thank you so much for powering through 2 of these today.
My pleasure. All right, well, I think we still have 50 people. So thank you so much for hanging on. I realize this is a big commitment, but every time we do this, I get more excited about the work, and I really appreciate everybody taking the time. So perhaps we can continue this. As I say, if you have questions, reach out to Zoe at fdl.ai. And we'll hopefully see you next time.
See you. Thank you.
Thank you very
Bye.
much.
Bye-bye.
Thanks.
Thank you. Thank you.
Bye-bye.